This lecture is for Physical Science, GNSC 1204 at Midwestern State University, and it's an additional piece of information I wanted to impart on accelerating from a standstill. So this gets us to a very important relationship that gets used a number of times and assumed in a number of our problems. Maybe we could just fast forward ahead and say, okay, let's not understand how we got this, but I think it's important, perhaps critical, to see that this isn't completely made up. We borrowed this from looking at specific systems that are accelerating from a standstill. So let's dive in. There's a number of applications for this. It's essentially a fundamental question we're trying to get at, is what if we started from a velocity of 0? And that is 0 in whatever units we're using. In SI units, that would be meters per second. We would say 0 meters per second. And I think it's important to remember that when you have a 0 value in this class, we're still going to consider the units attached to it. It's like the air in the half-filled glass. Don't take it for granted. So make sure you know that the units still apply even if we're talking about having no value or no magnitude whatsoever. If we're going to start at a velocity of 0 and then change it, that's an acceleration. Do this every day. If you drive and ride in a car, you have to start the car from a stop. Most of us come to our car parked somewhere, and we've got to move it. That's an acceleration to move it from that stop. But it also applies to dropping an object in a gravitational field, like we see every day, or throwing an object, which was an example of compound motion. So let's explore. Let's imagine that we have an automobile that's going to accelerate at 20 kilometers per hour per second. Now, kilometers per hour per second is a pretty messy unit for acceleration, but again, this gets us to a common problem we see every day. Let's imagine we're starting our car from a stoplight. It's at 0 kilometers per hour to start off with, and we're going to get so that we accelerate at 20 kilometers per hour per second and figure out what's happened to our car. Now, our car is going to accelerate, and we want to know how fast it's traveling after 3.6 seconds. And then the corollary to this is how far has the car traveled in that 3.6 seconds. So how fast and how far? That's what we want to know. And here's the keywords for our problem: if the car was initially stationary. So starting from a standstill. All right, we're going to do a calculation based on the acceleration, and we need to recall that accelerations are just changes in velocity over time. So changing the velocity and the magnitude of the velocity, the speed, is going to be what we're after. We know the acceleration, and we know the change in time. Those are given in the problem. They are up here. So I'm going to use my pen, and I'm going to circle those real quick. Our acceleration, if I can find it, nope, it's way up there, is 20 kilometers per hour per second. And our time is 3.6 seconds. All right, I'm going to need to manipulate this then, because what I don't really know is how fast, part one, how fast we were going. How fast is, how much velocity do you have? What was your speed? Remember, speed is the scalar and velocity is the vector. We're after, of course, the velocity, but we don't really need to specify that per se in this problem. So algebraically manipulating this, I can get this around by dividing both sides by, or multiplying both sides by delta t. That would help. So delta t on both sides, that gets rid of the delta t on the right side. Bam, you're gone. And now I've got a delta t, and then it's a matter of getting minus vi to the other side, because I know the initial velocity is 0 kilometers per hour. So that's just addition in algebra. We're going to add this to both sides. That takes away vi on this side, and that becomes a delta t plus vi. And then I'll just switch it around to put VF on the left side so that we can see it clearly. And this is the relationship we're after at this point. Now it's just plugging and chugging. We're going to take our acceleration, which is 20 kilometers per hour per second. We're going to multiply it by 30.6 seconds, which is our change in time. We're going to add it to the initial velocity, but the initial velocity is 0 kilometers per hour. So this whole thing really just doesn't count for us right here. We're done. We've got 72 kilometers per hour, and that is in units of velocity, so mission accomplished there. I can also solve the problem graphically if you'd rather do it that way. There is no wrong way to do this if it's going to get us the right answer. To do that, I need to set up a plot of time versus velocity, putting velocity on our dependent axis over here on the y-axis, and our independent variable of time. Time is hard to control. That sounds independent to me. We're going to put it on the x-axis down here. We know our initial velocity is 0. We also know that we have an acceleration of 20 kilometers per hour per second. And that gives us a rise over run of 20 kilometers per hour per second. In other words, I could just put a slope in here of 20 so that when I hit a velocity of 20, I am at 1 unit of time, which is a second. So I've drawn a nice little line in here to indicate that. That's the start of my line. And of course, then I can extend it out to 3.6 seconds. And voila, there we are. We're at 72 kilometers per hour for a final answer. So if you'd rather set it up graphically, that's an easy way to do it. Okay, part 1 asked, how fast are we going at the end of the acceleration? We got the answer. Our velocity final is 72 kilometers per hour. I'm showing it right here. There it is, right here. Now I want to answer part 2. How far has the car traveled in 3.6 seconds if we were initially stationary? There's a couple of ways to attack this, so bear with me. I'm going to go through 2 different methods. I think method 1 will probably be a fan favorite. I think it usually is, but it's important to show you method 2 as well. All right, first thing is how far have we gone is a distance thing. Where is the displacement in this? Where can we get displacement or distance? Well, certainly our velocity equation has it built into it. So let's algebraically manipulate that, and we get velocity times time. We need to ask which velocity we're interested in. Final, initial? No, we want the average velocity. So we're going to take the average velocity, and you might recall from earlier slides that the average we're going to take is just 1/2 of velocity final plus velocity initial. This actually works out of the statistical argument for averages, which is we can sum our observations or add our observations together and then divide by the number of observations. Well, we're just going to use 2 observations and we're going to sum those together. Plugging this in for our average velocity, our relationship now becomes our displacement is 1/2 velocity final plus velocity initial times delta t. Got a little problem here, and that is we've done delta t in seconds, but velocities in kilometers per hour. We got to make the time units work on this. So one easy way to solve that is turn velocity into kilometers per second. The other way we could do that is we could deal with time and hours. If you'd rather do that, it all works out in the wash because you'll get the same thing either way. But here's the conversion. If I want to get 72 kilometers per hour into 72 kilometers per second, I need to multiply it by 1 hour has 60 seconds in, or 60 minutes in it, and then 1 minute has 60 seconds in it. What this does is it basically says, okay, I'm going to multiply 1 hour by something over hours. That goes away. That's going to leave me with minutes, and then I'm going to get rid of the minutes, and I'm going to be left with kilometers per second as my unit. So a little dimensional analysis gets us to the right point. If I do this, if I, in other words, divide 72 by 60 and then divide it by 60 again, or multiply by 1 over 60 and multiply by 1 over 60 again, I will get 0.02 kilometers per second, or scientifically written, that's 2.0 e to the minus 2 kilometers per second. All right. So I'm going to put that in for my velocity final. that goes right here. I can convert velocity initial, but lucky for you, the mathematicians tell me that 0 times anything is still 0. So put any conversion you want in there, you're still going to end up with the 0 kilometers per second, because the nice thing about converting that one is 0 kilometers per second is the same thing as 0 kilometers per hour. That also means we're not really adding anything to 2 times 10 to the minus 2. We are just have the 0 term there. All right, if I multiply 2 times 10 to the minus 2 times 3.6 seconds, which is our change in time, and divide that by 2 or multiply by a half, I'm going to get the answer I'm looking for here. All right, before I calculate this out, let's just go through the answers real quick. So we're likely to have answers as a multiple choice phenomenon. And one thing we can do is say, well, you know, some of these just ain't going to work. Right? The question asks, how far has the car traveled? So I'm looking for units of distance. Yeah, kilometers is okay. So kilometers right there is okay. And kilometers right here is okay. Kilometers per hour, that's an acceleration. That's a velocity. That's not what we're after. And kilometers per hour per second is also the wrong units because that's an acceleration. We don't want that. So really it's between 120 and 3.6 times 10 to the 2. Okay, with the right dimensions inside, this actually becomes a really trivial problem if we think it through. We're going to take 2 as a very small order of magnitude, 0.02. We're going to divide it by half. This 2 is basically going to go away. It's going to be 1 times 10 to the minus 2. We're not adding anything here. We're going to multiply it by 3 to the 6. So really my work is done. It has to be answer E, but if you'd rather calculate it through to make sure that you've got that answer, let's go ahead and do it. So I'm going to enter in 2 exponential and then 2 and switch the sign on it, which is down there. So 2e to the minus 2, it's plus 0, so I don't have to worry about adding anything through it, but I am going to divide by 2, and then I'm going to multiply that by 3.6 seconds. And my answer is 0.036, otherwise known as 3.6 to the negative 2, and that should be in kilometers. My job is done here. Okay, there is another way to attack this, and this is a little more informative for what we're trying to do in the class, so I will go through it as well, but we're going to end up at the same place. I'll call this method 2, and again, the same question stands. How far has this car traveled in 3.6 seconds? So the velocity relationship seems helpful to us in this point. We'll want to use that. And again, manipulating for distance or displacement, we have v times dt or delta t. And then it's just a matter of figuring out what velocity we want. So we, again, want the velocity that is the average velocity. But this is where we're going to deviate. Basically, if velocity initial is nothing, then this is really just VF times 1/2, or VF over 2. And I can then move the 2 over the other side, and my final velocity is really 2 times the average velocity. That's all we're going to get out of that. We can then look at the acceleration relationship and realize that our acceleration should just be VF minus VI over delta t. And if VI equals 0, then acceleration is really just VF over delta t. And we already said that VF is the same as saying 2 average velocities. So let's just swap that in. And then I'm going to manipulate things around. In other words, divide by V on both sides and divide by A on both sides. And what I'll end up with is V over here, A times D, and divided by 2. So now we have a new velocity equation here, but keep in mind, you got to be careful with this one. This velocity relationship, which is an average velocity, is only applicable if we're talking about starting from a standstill. So you don't want to confuse this with the other ways we've just defined velocity. But if that's the case, then we can use a velocity that is a delta t over 2, acceleration times the change in time over 2. And that means when we plug that into our distance equation, this becomes delta t times a delta t over 2. That makes our delta t term squared. Now we can go and ask, well, are we ready to launch? No, the problem is that I've got accelerations in kilometers per hour per second, and my timing is in seconds. So I'm going to need to make an adjustment again. So we've done this before. 20 kilometers per hour per second can be multiplied by 1 hour over 60 minutes by 1 minute over 60 seconds. That leaves us with 0.056 kilometers per second squared, or you can write that as 5.6 times 10 to the minus 3 kilometers per second squared. Going to our distance relationship right here, we can plug that in. Our acceleration, 5.6 times 10 to the minus 3 kilometers per second squared, then can be multiplied by delta t squared, 3.6 seconds squared. Don't forget to square it. And times a half. We end up at the exact same place. But this is an important formulation of displacement, acceleration, and time for objects that start with no initial velocity. So that's why we did it this way. If you'd like to practice and have access to the slide set, or just want to use what's on the screen here, I've set up a practice problem where you can go through steps 1 and steps 2 using both methods to see what's happening, or you can just do it graphically for step 1 as well, because I showed you that. I've even cautiously written out the units here so you won't get lost there. See if you can arrive at the correct of the 4 answers below. And then here's part 2, method 1, set up so that you can just basically work through the blanks if you want to. I'd also encourage you to explore method 2, but it's going to end up at the same answer set when it's all said and done. So getting back to why I told you about method 2, it leads to a relationship here, 1/2 a delta t squared, or just more simply, t squared. That means if we know the acceleration and the time, we can find the distance that's involved, or we can rearrange to get it in another format. We can, of course, rearrange it to get into another format, so multiplying by 2 over a on both sides will get us to a point where we can move a and 1 over 1/2 a over to the other side with d. It becomes 2d over a equals t squared. Flip the sides that it's on, so t squared is now equal to 2d over a. If I'm just interested in t and not t squared, well, then I need to take the square root of both sides, and I end up with t equals the square root of 2d over a. Right, so this was the relationship we've been using to talk about accelerations from a standstill. This relationship only works for accelerations from a standstill, but fortunately for us, that's quite a bit of stuff we want to talk about. Not just cars starting from a red light, but also thinking about how altitudes or heights change, that should be an h, when you're talking about accelerations due to gravity, or little g. So our acceleration could be the acceleration due to gravity, and that means a change in displacement that relates to a change in altitude. You can see this not only in just dropping objects, but also in throwing objects like baseballs.